Hello everyone, this is Jay from BTYT Tech Library. Today we are going to do ethical hacking on HackTheBox Fireflow machine for educational purposes. This box right here is a cracked map that will definitely test your penetration testing skill, but every single attack plan sets up the chain for the tactical kill. We are going to abuse a new flow in langflow, specifically CVE 2026-33017. Splitting open the initial foothold so clean it almost feels like tech heaven. From there, we dig deep and sweep through the environment, catching a leaked credential stream, sliding smoothly through the inside network just like a hacker in a dream. Next, we target the MCP server where the actual token validation is extremely lean, bypassing the mechanism forging none on the screen. With that bypass, we register a malicious tool for an immediate run, crossing the Kubernetes path before the defensible logging has even begun. And for the final stage, we abuse the node and proxy permissions to complete our climb, slipping straight to a privileged path to snatch that root flag right in time. Let's hack this box. First, let's roll in the Rust scan. We found two ports open, 22 and 443. Through the result, we can assume that there might be additional vhosts that exist. For now, update our host file and visit the website while running the robust background. Yeah, we can tell this is the ACP MCP related service. And before we visit, don't forget to update our host file. What? Okay, let me just... Before we jump in, let's quickly break down what this vulnerability is and why it's so dangerous. First, what is langflow? It's an open source visual tool that lets developers build AI pipelines and LLM applications simply by dragging and dropping components. The flow we are looking at is CVE 2026-33017, which scores a critical 9.8 out of 10 on the severity scale. It allows unauthenticated remote code execution. In plain English, a hacker can run malicious code on your server without even logging in. So how does it actually work? The root cause lies in Langflow's public sharing endpoint, called build public temp. This endpoint is designed to let anyone view a shared AI workflow without logging in. But there is a fatal mistake. When a request is made, Langflow allows the user to send custom flow data. A hacker can abuse this by crafting a malicious request packed with arbitrary Python code. Instead of using the safe data stored in the database, the server blindly accepts the hacker's input and pass it directly into a dangerous Python function, exec. With zero sandboxing or security filters, the server executes the hacker's code instantly. This isn't just a missing login screen, it's a complete lack of input validation on a public door. Now that we know the theory, let's do it. By replacing the file writing code with a reverse shell payload, we can gain direct access to the target system. Before we continue, let's talk about how to fix it. The most effective mitigation is simple: upgrade immediately. If you are running Langflow version 1.8.2 or earlier, you are exposed. You must update your environment to version 1.9.0 or later right away. If you can't upgrade immediately and need a manual fix, the underlying solution is remove the data parameter from the public endpoint. Public flows must only execute safe data stored in the database. Never unauthenticated attacker-supplied data. In short, ensure that any unauthenticated request can only reach the safe build graph from DB path, closing the backdoor for good. Good. Now we are in. We owned www-data user. Let's quickly check where is the user flag. Nothing? Or we can't read it? There is a user called Nightfall. Let me check environment variables. Tell me about it. We know which file to check. Cool. Based on our findings, let's set up SSH local port forwarding to access the internal network from our environment. You know, we just found a critical attack vector here, but let's save it for now and come back to it later. Great. Right here, we have a very pretty looking Swagger style API schema document. First, we have post/API/version1/auth. This is a login endpoint. When a user sends their credentials here, the server verifies them and returns a JWT for authentication. Next is get API v1 tools. This endpoint allows you to retrieve a list of all currently registered tools in the system. Third, we have post API v1 tools. This is used to register a new tool. Finally, there is post/MCP. This serves as the JSON-RPC 2.0 endpoint. It is a specific address you call whenever you need to invoke or execute one of the tools. As you might have guessed, our first pick is authentication. Good. With this, we can act as a langflow bot user when we make a request. As next step, we are going to register a new tool which is connecting reverse shell to our Kali machine for infiltration. Hey Bruno. Oops, it looks like tool registration requires admin privileges. While it's a bit disappointing, it confirms one important detail. An admin role actually exists within their authentication system. Now it's time to work back to what we discussed earlier. If you ever built a modern web app, you've probably used JWTs, JSON Web Tokens, to handle user logins. They are super popular, efficient, and widely adopted for a reason. But today, we are breaking down a classic configuration oversight that can unexpectedly weaken your authentication system. It's known as the JWT non-algorithm attack. First, what exactly is a JWT? Think of a JWT as a digital ID card that the server gives your browser after you log in. It consists of three parts separated by dots: the header, the payload, and the signature. The header, red, tells the server what kind of token this is and what algorithm was used to lock it, usually something like HS256. The payload, blue, contains the actual data, like your ID or username. The signature, green. This is the most critical part. It's a secret cryptographic seal. The server creates it using a secret key to ensure no one has tampered with the token. If an attacker changes the user ID in the payload, the signature becomes invalid, and the server says, hey, this ID card is fake, and kicks them out. But here is where things go wrong. In the official design specifications for JWT, creators actually built in an option called the non-algorithm. You might ask, why on earth would anyone design a secure token with a non-algorithm option? Well, it was originally meant for two specific reasons. First, for debugging and testing during development, so developers didn't have to deal with crypto keys while fixing code. Second, it was designed to support use cases where the JWT contents, is already secured by other means, even without applying a signature or encryption to the JWT itself. For example, if the token is passed inside an already encrypted trusted inner network. The intentions were good, but it unintentionally created a significant blind spot if the backend isn't configured correctly. In a non-algorithm attack, a malicious hacker takes a normal user's token and modifies it. First, they decode the header and change the algorithm parameter from HS256 to none. Second, they alter the payload, changing their user ID to admin. Finally, they completely delete the signature, leaving the trailing dot. If the backend server is poorly configured, it reads the header, sees algo none, and says, "Oh, the spec says this is allowed. No signature needed, welcome admin." Just like that, the hacker completely bypasses authentication and gains full access. It sounds crazy, right? But this vulnerability has brought down massive corporate systems. So how do we fix it? First, explicitly restrict allowed algorithms in your code. When your backend application decodes a JWT, never let the library guess the algorithm. Pass an allowed list like algorithms HS256. If a token arrives with none, the library will instantly reject it. Also, keep your libraries updated. Most modern frameworks disable none by default now. Second, you can also take a look at an interesting alternative called Passeto. While JWT remains the industry heavyweight, Passeto, which stands for Platform Agnostic Security Tokens, is gaining a lot of traction for new projects. Unlike JWT, which lets developers choose dangerous algorithms like none, Passeto eliminates user choice entirely. It uses strict predefined secure protocols. With Passeto, you literally cannot make the non-algorithm mistake because it's designed to be secure by default. Okay, back to business. This time, let's use sudo admin token and register our rev shell tool. Cool, now we can see our tool is registered correctly. As a final step, let's call our tool and get a shell. Okay, we're in. What? What the? Ever had your Python reverse shell open successfully through an API payload, only to die a few seconds later for no obvious reason? You didn't even close your terminal, but the connection just drops. This happens because the backend API process finishes its execution and terminates, taking your reverse shells down with it. To fix this, we can upgrade our classic one-liner to break away from the parent process entirely. Take a look at this snippet. It uses OS fork and OS set as ID to background itself permanently. Cool, now we are really in. Okay, I think we are in the Kubernetes part. But fear not, Kubernetes is dominating modern infrastructure right now, making this an excellent learning opportunity for us. And just a side note, this box is copy-failed proof. I tried that earlier. I hoped it might open up via an easier vulnerability, but no luck. Alright, time to hunt for Kubernetes service credentials. By default, the token to talk to the Kubernetes API server is auto-mounted inside the pod. You can find it on the /var/run/secrets. It usually consists of 3 files. The token file, which is a JWT token for API auth, the ca.cert file to verify the API server connection, and the namespace file containing the current pod's namespace. Also, if developers mounted sensitive data into the pod using Kubernetes secret objects, you might find them on the /etc/credentials or /secrets. As you know, the token file is actually a JWT for API authentication, so we can easily decode it to see what's inside. Since the machine we are in doesn't have a kubectl, we are going to route our traffic through a SOCKS proxy and use kubectl right from our Kali machine to exploit it. By the way, I actually tried this with legalo-ng earlier, but the kubectl auth cni command just wouldn't go through. It seems like Legalo's L3 tunnel mechanism might be handling these heavy Kubernetes API calls differently, probably causing some packet drops. Since we are not diving deep into that today, we are just gonna use SOCKS 5 connection to keep it moving. Sweet. Let's check what we can do with kubectl. Let's see. Having get permission on node/proxy is classified as a high-risk vector for a total cluster takeover. Simply put, the single permission allows an attacker to bypass authentication entirely, hijack an entire work node, and intercept data from every single pod running on it. To understand why, look at how Kubernetes is built. Every work node runs a management agent called a kubelet, typically on port 10250, which requires its own authentication. However, for administrative convenience, the master API server provides a proxy feature that forwards requests to the kubelet via the API/v1/nodes/node-name/proxy path. This means if an attacker gets get permission on nodes/proxy, they can use the API server's own authority as a shield, directly calling any sensitive kubelet API without needing any authentication at all. Next, we perform recon for high-value targets. Using kubectls get _row, we query the proxy endpoints for all running pods on the node named Fireflow. We pipe the JSON output into a JQ to clean it up. Looking at the namespaces and pod names, we spot a monitoring app. In Kubernetes, monitoring agents usually run with high privileges, making it our primary target. Since the Kubernetes API server returns data in a structured JSON format, its schema is completely standardized. This predictability is exactly why we can use JQ to target and extract the precise values we need every single time. Final step is exploitation via stream upgrade. We construct a row call request to establish a WebSocket tunnel directly to the kubelet exec endpoint. By specifying the v4.channel.kubernetes.io protocol header, we successfully bypass standard RBAC restrictions and execute arbitrary command such as ID inside the monitoring container. Here's the takeaway for clustered means. Locking down pods and secrets isn't enough. Many teams unintentionally leave the backdoor open by misconfiguring sub-resources like nodes/proxy. It's a favorite trick for pentesters because it shows how an attacker with zero pod permissions can still hijack the node. If you haven't audited your sub-resource RBAC lately, this might be your sign to take a quick look. So how do we fix this? It's actually pretty simple. Just review your cluster roles and make sure nodes/proxy isn't grouped in with general read-only permissions. If your team doesn't explicitly need to proxy into the kubelet, just remove the nodes/proxy sub-resource from the rules array entirely. Cutting down these RBAC permissions is all it takes to close this backdoor. That's it. We just went through a ton of heavy concepts and cool exploits today. I highly recommend you taking a step back to digest all these attacks and mitigations. It might feel like extra work, but it's a huge time saver in the long run. Stay safe, take care, and I'll catch you guys in the next one.